Okay, so I will share my screen. Okay, can you see my screen? Can you hear my voice?
Yes, Doctor.
Okay. Okay, so last we have gone through chapter 5 about the
Dr. share slide ke?
kejap eh. Belum eh? Sorry.
Belum.
Ya. Okay. 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 Nampak slide eh?
Nampak?
Okay. So last week we have gone through this topic about the transmission line characteristics. Okay, so where are we now? So if I draw the whole picture of transmitter and receiver, okay, so for example, we have here the transmitter, okay, and channel, okay, and then we have the receiver, okay. So we also have the wired transmission line, okay. So basically, the transmission line explain about the medium or the channel that connect the transmitter and the receiver, okay. So for the transmission line, there are guided transmission line for wired communication, and also unguided transmission line for the wireless medium, okay. So basically the word transmission line in your lecture notes explains about the channel or the medium that connects the transmitter and the receiver. So it can be wired, it can be wireless also, okay. So for the transmission line characteristic, there are three important things. The first one is the characteristic impedance. We call it as Z0. And then velocity factor, VF. And another one is the standing wave ratio, okay, SWR. Okay. And we have seen the transmission line parameters. Okay, so the transmission line or the wire, the cable can be represented in terms of lump elements, in terms of resistance, inductance, capacitance, and conductance. We can draw the transmission line in terms of these lump elements. Okay, so basically the transmission line consists of elements of resistance, inductance, capacitance, that are repetitive, okay, over a long transmission line. So imagine that if you have a long transmission line, we can represent this transmission line in terms of this resistance, inductance, capacitance, and conductance. Okay, so later in the final exam this semester, you will be asked to draw the transmission line using the lump elements. Okay, so basically these are the things that you need to draw during the final exam. Okay, repetitive construction of R, L, G, and C. Okay, for the whole transmission line. Okay, so this will come out in the final exam. And then so different kind of transmission line, different kind of cable or wired transmission line. There are specific formula in order to calculate how much is the value of resistance, the value of inductance, conductance, and capacitance. So these are the specific formula, but you don't need to memorize this, okay? So all the given formula needed for the final exam will be given in the final exam, okay? At the end of the question, there are going to be a list of formulas given to you during the final exam. And this is the skin effect. Skin effect happens when the radio frequency is very high, okay, in terms of gigahertz, for example. So the current tends to flow in the surface of the conductor rather than at the core of the conductor. So this is the skin effect. Okay, the phenomenon that happens when we use a high frequency transmission, and this happen along the transmission line. Okay, so we actually at the beginning the wave travel at the core of the conductor, but as the frequency is very high, the wave tends to look as if it travels along the surface of the conductor. Okay, and we also have seen about this characteristic impedance. Okay, so characteristic impedance, this is two pictures. So imagine that this is a picture A and the other one is picture B. So this is a different picture. Okay. So characteristic impedance is actually an input impedance for a long transmission line. Okay. So picture A is for a long transmission line, infinite length of transmission line. Okay. So the characteristic impedance Z0 is actually the input impedance seen looking into a long transmission line. Okay, so regardless of the length of the transmission line, the characteristic impedance is the same. Okay, and if we look, if I repeat again, the characteristic impedance is the input impedance for a long transmission line, picture A. Okay, and if we look into picture B, so picture B, imagine that we have a finite length of transmission line. Okay, so for a finite length of transmission line, the input impedance is uh, is an impedance, okay, equal to the load impedance, assuming that there's no losses in the transmission line. Okay, so the the characteristic impedance is equal to the load impedance for a finite length transmission line. And this is a lossless transmission line. So why you might assume why we need to make the load impedance similar with the characteristic impedance? Why is it need like that? So in order to do why do we make like this is so that the transmission line is a lossless transmission line, means that all the wave transmitted from the source will be transferred to the load without reflection. There's no reflection to the source back. So that's why for a finite length transmission line, the characteristic impedance is equal to the load impedance. Okay. So this is to ensure that there's no reflection in the transmission line. All the wave travels from the source to the load will be absorbed by the load without the reflections. Okay, so transmission, the characteristic impedance in general, we can say that it is actually the ratio, okay, of voltage and current of the wave that travels along the transmission line. Okay, so basically Z0 is equal to the V versus I. Okay, this is a general equation for the impedance. Okay, the voltage, the ratio of voltage over current of the wave that travels along the transmission line. But in this case, we look the transmission line into two categories for finite length and also infinite length. Okay, and for your information, characteristic impedance is not depending on the length of the transmission line. Regardless of the length of the transmission line, the characteristic impedance is still the same. And the unit is in terms of ohm. Okay. So you see that for a maximum power transfer from the source to the load without a reflection, the transmission line must be terminated in a purely resistive load equal to the characteristic impedance. Okay, so that means there's no reactance parameter in the transmission in the characteristic impedance. Okay, so characteristic impedance, okay, if you see the value, okay, it is normally within 50 to 75 ohms. Okay, so normally we see the values is within 50 to 75 ohms, and you see that the characteristic impedance is a purely resistive values without the reactance. Okay, if you know that the impedance normally we write in terms of x, uh, a value a plus a plus j of b, right? So z, normally we write the impedance in terms of uh, what we call the resistance plus the reactance. Okay, but um, for the case of characteristic impedance, it is purely a resistive value without the reactance. Okay, so it is a value in terms of ohms. Okay, and it is fixed throughout the transmission line. Okay, and this is a section of the transmission line. If we take one section of the transmission line and we put the source on the left side and the load on the right side. Okay, so this is just to show you that if you want to make sure that a maximum power transfer from the source to the load, we must make the load to be equal to the characteristic impedance. Okay, so we must make sure that ZL, the load impedance, equal to the characteristic impedance if we want to make sure that all of the power from the source is absorbed by the load. Okay, if the load impedance is not equal to the characteristic impedance, that means there are going to be some losses. Okay, so the terms losses here means a reflection, okay, a power reflection from the load back to the source. Okay, and we're going to see about this phenomenon later, okay, after this. Okay, so in order to ensure a maximum power transfer, we must make sure that the load impedance equal to the characteristic impedance. Okay, so all the power from the source absorbed by the load. Otherwise, there's going to be reflection. Reflection means losses. Okay, so characteristic impedance can be calculated using these equations. Z0 equal to R square root of R plus J omega L divide over G plus J omega C. Okay, and we can see we can simplify the equation for two extreme cases. The first case is when using low frequencies. Low frequencies here means a few kilohertz and below. Okay, so if the frequency of transmission, okay, we are talking about frequency of transmission is low, so we can simplify the equations to become characteristic impedance equal to R square root of R over G. Why is it like this? Because in a low frequency transmission, the reactance parameter, okay, the reactance is this one, J omega L and J omega C, is can be said as very small and can be omitted. So that's why we can simplify the equations to be approximately equal to the square root of R over G. The unit is still in terms of ohms. Remember that characteristic impedance, the unit is in terms of ohm. And if we use the high frequency transmission, okay, the resistive components would be very small compared to the reactance component. Okay, so that's why we can simplify the equation to become Z0 equal to square root of L over C. Inductance divide with the capacitance. Okay, so high frequency here normally within the range of megahertz towards gigahertz and so on. Okay, so normally in the radio frequency transmission, we can simplify the equation to be like this, square root of L over C. And characteristic impedance also can be defined as E over I. E is the source voltage, I is the current that flows along the transmission line. Okay, so how many equations that we have seen here? This is the first equation, the complete equation, the second, the third, and the fourth equation. Okay, so there are many ways to calculate the characteristic impedance. Okay, and this is example for a two-wire parallel transmission line with an air dielectric constant. Z0 can be determined from its physical dimension. So this is for a two-wire, okay, two-wire parallel transmission line, or we can say that this is a guided transmission line. Okay, so the first one is to find the characteristic impedance. So for a two-wire transmission line, the equations is this one. Okay, so this equation is specific for a two-wire parallel transmission line. Okay, so it is equal to 276 log D over R. D is the distance between the centers of two conductors. R is the radius of the conductor. So it is actually equal to like this. So the picture on the left. Okay, so D is the distance between two conductors. Okay, this is the distance between two conductors. Okay, this is the conductors. So the distance between conductors is D, and the radius of each conductor is R. Okay, this is R. And another one for a coaxial cable. Okay, coaxial cable is a single conductor transmission line. So the characteristic impedance can be calculated as 138 over square root of epsilon R log D over D. Okay, so capital D is the diameter of the insulating material in terms of meter, and small d is the diameter of the inner conductor in terms of meter, and epsilon R is the dielectric constant of the insulating material. So epsilon R is depending on the type of insulating material. Okay, and this is it, the picture of coaxial cable. Okay, D is the diameter. Okay, capital D is the diameter of the insulating material, the whole cable. Okay, so this is the whole cable diameter, and small d is the diameter of the conductor, and epsilon R here is the dielectric constant of the material. Okay, and for your information, this coaxial cable will come out in the final exam later. Okay, so there is a sub question about coaxial cable given in the final exam, and this equation also will be given in the final exam. Okay, 138 over square root of epsilon r log d over d. Okay, so if we go through the example, okay, so the first one is about two-wire parallel transmission line. Okay, so determine the characteristic impedance. If you are given the ratio of D over R equal to 12.22. Okay, so therefore characteristic impedance is equal to 276 log D over R. So this is actually D over R, which is equal to 12.22. So we get 300 ohms. And another example for a coaxial cable. Okay, so in this example, you see that the parameter given to you is not in terms of international standard, okay, SI unit. So this example use inches instead of meter. Okay, so I can say that this example is taken from the American literature books, where they use inches, feet, miles, and so on. Okay, but um, in our exam, in the exam later, you will be given in term of SI unit. Okay, the length will be given in term of meter. Okay, so don't worry. For this example, we can use inches. If we use inches, that means all the length should be in terms of inches, so that we can get the same answer. Okay, so determine the characteristic impedance for an RG59A coaxial cable. So this is the type of coaxial cable. So coaxial cable has many types, many codes with different parameters. Okay, so RG59A coaxial cable with the following specification. The diameter of the conductor is 0.025 inches. D, the diameter of the whole cable is 0.5 inches. Epsilon R, so please correct your notes. This is supposed to be a subscript of R. Okay, so epsilon R equal to 2.233. Okay, so characteristic impedance for a coaxial cable is equal to 138 divided with square root of epsilon R. So this is actually the value of epsilon R log D over D. Okay, so this is D over D. Okay, so if you put the values, so in this case, we are still using the inches value. Okay, doesn't matter. If you use inches, make sure all in terms of inches. If you need to use meter, all parameters should be meter. And we're gonna get the same answer actually. Okay, so the value here is 71.9 ohms. Okay, if you calculate the value is around 71.9 ohms. Okay, so the question in the final exam later is something similar with this example. Okay, so we just change the values. Okay, given in the final exam, the values will be different. So basically, the answer is the way you write the answer is something like this. Okay, later. So make sure you practice this example for your final exam. Okay. And another example, determine the characteristic impedance for an RG coaxial cable, RG59A coaxial cable. Okay, with the following specification: inductance parameter. Okay, the inductance is 0.118 microhenry per feet. Okay, so this example use feet in terms of instead of meters. Okay, and the other one capacitance parameter is 21 picofarad per feet. Okay, so determine the characteristic impedance. Okay, so now you are given L parameter and C parameter. Okay, it doesn't specify whether this is a high frequency, low frequency, or anything. Okay, so you are not given the parameter of R or the parameter of G. Okay, so therefore, in this example, it assumed that it used a high frequency transmission line. So if a high frequency transmission line, we can simplify the characteristic impedance equation to become Z0 equal to square root of L over C. So this is given previously. If you see, if I go back to the previous slide, okay, so for high frequency, the inductance and capacitance are dominants when you use a high frequency. When we use a low frequency, the resistance component are dominants. Okay, so in this case, in this example, you are given L and C parameters, so we can straight away use the L and C parameter. Okay, so therefore, square root of L over C. So we can put a square root of 0.118 microhenry per feet. And another one is 21 picofarad per feet. Okay, so if we use a feet over feet, okay, so we can cancel out the distance parameter. Okay, so this is actually 0.118 microhenry per feet. Okay, divide with 21 picofarad per feet. Okay, so actually we can cancel out the feet parameter. So therefore it is microhenry divided with picofarad. So you can get in terms of ohms. Okay, 75 ohms. And another parameter is the propagation constant, which is we call it gamma, is equal to alpha plus j beta, where alpha is the attenuation constant. Okay, alpha is the attenuation constant, a function of distance which determine how the voltage or current decrease with the distance along the transmission line. The unit is in terms of Nepers per unit length. Okay, another one is beta. Okay, beta is a phase shift parameter. Okay, phase shift constant parameter, and it is a function of time, a distance, and determine the phase angle of the voltage or current variation with distance when it travels through the transmission line. Okay, so the phase shift parameter beta, okay, is equal to 2 pi over lambda. This is the first equation for beta. Okay, and the other equation for beta is this one. Okay, omega times square root of LC. Okay, so this is actually 2 pi f square root of LC. Okay, f is the frequency of transmission. Okay, the frequency of transmission. Okay, so this is the second equation. So actually we have asked these parameters also in the final exam in the previous semester. Okay, where we give you the frequency of the transmission, we give you the L parameters, inductance parameters, and also the capacitance parameter of the transmission line. So from there, the students can calculate the phase shift constant parameter, okay, the beta parameter. And we're going to see the example later after this, okay. So the other parameter, okay, the other parameter is wave propagation, okay, is velocity factor. Okay, velocity factor is known as the velocity constant defined as the ratio of the actual velocity of the propagation through the given medium divide with the speed of light. Okay, so you see that velocity factor, okay, velocity factor is equal to Vp, phase velocity, divide with the speed of light. Okay, so Vp is actually Vp is the actual speed of the wave that travel through the medium. C is the speed of light. Okay, so Vf, the ratio of Vf is actually larger than 0, okay, and less than 1. Okay, so Vf would be equal to 1 if the wave travels in the free space or the vacuum. Okay, if the transmitted wave travels in the vacuum, we can say that the speed of the wave is equal to the speed of light, and the Vf is equal to 1. Okay, so if Vf is equal to 1, that means the transmitted wave has the same speed of the speed of light. Okay, so this is the first equations of Vf, velocity factor. Okay, velocity factor is the value is more than 0 and less than or equal to 1. Okay, and the second equation to calculate the velocity factor is this one. Okay, Vf equal to 1 over square root of epsilon r. Okay, epsilon r is the dielectric constant, or simply the relative permittivity of the material used for the transmission line, for the cable. Okay, so we're going to see this epsilon r parameter later, depending on the type of cable that we use. Okay, depending on the material used for the for this cable, the electric constant. And another parameter is determine the phase velocity or the speed of the wave. Okay, so Vp is the phase velocity or the speed of the wave that travels along the medium, which is equal to 1 over square root of Lc. Okay, so you can also calculate Vp using these equations. So Vp is equal to Vf times the speed of light. Okay, and we can also calculate Vp in terms of inductance and capacitance. Okay, if you're given in terms of inductance and capacitance of the transmission line, we can calculate the speed of the wave that travel inside the transmission line. And this is it. Okay, the velocity factor and also the dielectric constant. Okay, so the velocity factor Vf, if you see from here, there are different kind of materials for the medium. Okay, for the type of medium, from vacuum, air, Teflon until glass. You see that the velocity factor in vacuum is equal to 1. And as we move to different kind of materials for the transmission line, the velocity factor decrease, okay, until 0.3651 for type of glass. That means the wave that travel in a glass medium, it moves much slowly compared to the speed of light. Okay, and another one, if you see that the electric constant epsilon r, it becomes increased, okay, from vacuum to different kind of materials. Okay, the lowest dielectric constant parameter is in vacuum, which is equal to 1. And as we use a different kind of epsilon r, different kind of medium, okay, the dielectric constant becomes higher. Means that the medium has more dielectric. It's become dielectric compared to the conductance. Okay. And this is it, the example 4 of a coaxial cable. Okay, so this is also a good example for the final exam. Okay, so an RG59A coaxial cable operates at a frequency of 900 megahertz. Okay, has the following specification: L 0.118 microhenry per feet and capacitance is 210 picofarad per feet. Calculate the following. Okay, so I suggest that you change the frequency over here. Okay, change it to 300. So change it to 300 megahertz. Why? Because the answer is given in terms of 300 megahertz. So change the question so that it in line with the answer. Okay, so use a 300 megahertz of the frequency. Okay, so the first question asks you to find the sorry, I cancel this one, so become 300. So the first question asks you to find the phase constant beta parameter. Okay, so beta parameter, based on the previous example, is equal to omega times square root of LC. Okay, omega is 2 pi f. Okay, omega is 2 pi f times square root of LC. Okay, so 2 pi f. Okay, so we already changed the frequency in the question to become 300. Okay, multiplied with L and C. Okay, 0.118 microhenry per feet, and the other one is 210 picofarad per feet. Okay, so remember in this example we use the length in terms of feet. Okay, later in the exam we give you in terms of meter. Okay, it doesn't matter, it's just a different ratio. Okay, the answer will be the same. So here, since we use a per feet, that means our answer should also be in terms of per feet. Okay, because we use a microhenry per feet and also picofarad per feet. So the inductance, the reactance parameter, L and C reactance parameter, is given in terms of length. Okay, so that's why our answer should be in terms of length, the same length also. Okay, so therefore, in this case, we're gonna get 9.38 radians per feet. Okay, since we use per feet in the value, so the answer also in terms of feet. Okay, so if you see the previous slide, okay, so this is um, radians per unit length. So you see that the value of beta is radians per unit length. Okay, the unit length that we use in the example is in terms of feet. So that means it is radians per feet. Okay, so if you go through the example, so it is a radians per feet. If the question give you in terms of per meter, so you should use per meter. Okay, the second question asks you to find the velocity on the transmission line. So this is to ask you to find the value of VP, phase velocity, the actual speed of the wave that travel through the transmission line. So this is equal to 1 over square root of LC. Okay, since we are given L and C parameter, so we can use it, okay, to calculate the velocity. Okay, so 1 over square root of 0.118 microhenry per feet times capacitance 210 picofarad per feet. Okay, so since we are given the values of length in terms of feet, so therefore the answer should be feet per second. Okay, so if we use a standard unit, it should be meter per second. So don't be confused. Don't be confused. So this is the speed. The unit for speed for standard SI unit is actually meter per second. But in this case, we are given the parameter in terms of feet as a length. So we have to use it. Okay, so it is actually feet per second. 2 times 10 power of 8 feet per second. Okay, so I believe that the answer has a few decimal points. The answer has a few decimal points. So in this example, it has simplified to becomes 2 times 10 power of 8 feet per second. Okay, so class, if you have a question you want to ask, please ask questions. Okay, I will try to explain it to you. Okay, then what? Then the question asks you to find the dielectric constant of the coaxial cable. So the question asks you to find the epsilon r. Okay, so epsilon r, we can find it through a velocity factor parameter. Okay, so epsilon r, actually we can find it using these equations. Vf equal to 1 over epsilon r. From here, we can find the epsilon r parameter. Okay, so before that, we need to find the Vf. Okay, the ratio of Vp over speed of light, the ratio of the wave velocity over the speed of light. Okay, so Vf is equal to the speed of the wave divided with the speed of light. Okay, so 2 times 10 power of 8 divided with 3 times 10 power of 8. So we get, so this is the standard speed of light. So we get 0.6666. Okay, and therefore, okay, when we want to find the epsilon r, okay, so epsilon r is actually equal to, epsilon r is equal to 1 over Vf square. Okay, so you're gonna get 2.25. Okay, so you can use your calculator. Okay, so 1 over 0.666. Okay, and then square, so you're gonna get 2.25. Okay, okay, can I get your response? Are you still there?
Yes, Doctor.
Yes, Doctor.
Okay. Okay, so if you have question you can ask. Okay, otherwise we're gonna move to the next topic. Okay, okay, so if no question, I will move to this next topic, which is about the standing wave. Okay, so standing wave, in Malay we call it as gelombang berdiri. Okay, so standing wave, you're gonna see later that at a, if we freeze the time, okay, if we freeze the time, okay, at a specific time, we might see that the wave looks as if it stands on a flat surface. Okay, so that's why the terms standing wave, as if the wave stand on a flat surface. Okay, seolah-olah gelombang itu berdiri di atas permukaan yang rata. Okay, so standing wave happens when the load impedance not equal to the characteristic impedance. Okay, so before we go through this, so we have to see this picture first. So this picture shows the source and the load connected using a transmission line, a wired transmission line. So the wave that travels from the source to the load, okay, is called as incident wave. And the other one, the wave that travels from the load to the source, this is what we call as a reflected wave. Okay, and in order to understand this, okay, so we have here the load is ZL. Okay, and the transmission line here has a characteristic impedance Z0. Okay, so you see that if, okay, if Z load equal to the characteristic impedance, that means all the incident wave will be absorbed by the load, and there's no reflection. Okay. And the second scenario is when, okay, I delete this. The second scenario is when the load impedance not equal to the characteristic impedance. So what happened? Okay, if the load impedance is not equal to the characteristic impedance, that means some or all of the incident wave will be reflected back to the source, okay, as a reflection. Okay, only if the load impedance not equal to the characteristic impedance, there's going to be reflection. Some or all of the incident wave will be reflected back to the source. Okay, so in Malay, I can say that sekiranya karakteristik impedance tidak sama dengan load impedance, maka sebahagian atau keseluruhan incident wave akan dipantulkan semula kepada source. Okay, so this reflection is actually a losses. Okay, a loss. Okay, the reflection is actually a loss. Okay, ideally, we want all the incident wave to be absorbed by the load. Ideally. However, when the load impedance not equal to the characteristic impedance, there's going to be reflection. Okay, so the reflection wave is what we call as a reflected wave. Okay, it goes back to the source. Okay, so this is the losses that happens inside the transmission line. Okay, so you see that standing wave only happens when the load impedance not equal to the characteristic impedance. If the load impedance equal to the characteristic impedance, that means there's no standing wave. Okay, so standing wave happens due to this imperfection. Okay, if the ZL, if the load impedance not equal to the characteristic impedance, then the standing wave will happen. Okay, so standing wave is actually the sum of incident and reflected wave. Okay, the summation of incident and reflected wave will be equal to the standing wave. Okay, which is this one. Okay, so you see that in order to understand the standing wave, okay, we should see these three graph over here. The first one, picture A, shows the incident wave, the wave that travels from source to the load. This is the incident wave. The second graph shows the reflected wave. Okay, the wave that travels from load to the source. Okay, so this happens because the load impedance not equal to the characteristic impedance. Okay, so there's a reflection, and you see that the summation, okay, the summation of incident wave and a reflected wave would be equal to graph C, what we call as a standing wave. Okay, standing wave is the summation of incident and reflected wave. Okay, and there's a few parameters in the standing wave that you should understand. The first one, it has a minima. Okay, minima is this one, the minimum value. The minimum is not zero. The minimum is not 0 actually. It has a value. Okay. The minima is what we call as nodes. Okay. And the other one, it has a maxima. Okay, so the maxima is a maximum value, what we call as antinodes. Okay. And another parameter is said that each of these nodes or antinodes is separated by half wavelength. That means the distance is lambda over 2. Okay, the distance is lambda over 2. Similar with this one, between antinodes is also lambda over 2. Okay. Okay. So lambda over 2 is the distance from from two antinodes or two nodes. So the nodes are separated by lambda over 2. Okay, the distance. So this is the animated graph, the animated graph to show you about the standing wave. Remember that standing wave, we can only see the standing wave if we freeze the time. At a specific time, we freeze the time, and we're going to see that the wave looks like as if it stands on a flat surface. So you see that if you see from this graph, graph color yellow move from left to the right. Okay, we can say that it moved from the source to the load, while the other graph, the gray color graph, move from load to the source, from right to the left. Okay, and the purple color graph is actually the standing wave. Okay, the purple color graph is actually to show you about the standing wave. Okay, so you see that when the incident wave and reflected wave were at the same location, okay, we can see that you can see the standing wave. You see that, okay, so the standing wave happens now, and then again, and then again. So you see that when the incident and reflected wave cross the same locations, there's going to be the standing wave. Okay. So if standing wave happens, okay, if standing wave happens, which means that characteristic impedance not equal to the load impedance. Okay. So standing wave happens, happen. So when standing wave happens, we can measure some parameters, some important parameters. Okay. Remember, when standing wave happens, that means there's going to be reflection because the load impedance not equal to the characteristic impedance. Okay. So if reflection occurs, that means there's going to be a reflection coefficient. Okay. So reflection coefficient is the ratio of reflected voltage divided with the incident voltage, or reflected current divided with the incident current. And there's no unit. It's a unitless parameter. Okay. And this is it. Okay. The three extreme cases. So these will come out in the final exam. Okay, this will come out in the final exam. You will be asked to calculate the load impedance. Okay, for these three extreme cases. Okay, you'll be asked to calculate the reflection coefficient in these three extreme cases. Okay, so what are these three extreme cases? Okay, So there are going to be three extreme cases. Three extreme cases is like this. The first one, I like to show the first one is going to be the what we call as a match. So we begin below, so that easy for us. So the first case is when Z load, okay, load impedance equal to the characteristic impedance. Okay, let's say that this is the first one, what we call as a match transmission line. Okay, the first scenario is match transmission line, where the load impedance equal to the characteristic impedance. If this happens, that means there's no standing wave. Okay, so if load impedance equal to the characteristic impedance, that means all the transmitted wave, all the incident wave will be absorbed by the load, and there's no reflection. If no reflection, that means no standing wave. Okay, no reflection. Perfect. Match transmission line, match circuit. Okay. Then we go to the second extreme cases. Okay, which is during the open circuit. What does it mean by open circuit? So open circuit, in Malay we call it as a litar buka. Okay, so imagine that this is a source side, source, and this is the load. Okay, so at the load side is a open circuit. Okay, that means the load is very high, infinite value. Okay, so if this happen, of course, ZL not equal to the characteristic impedance. And what happened? Okay, if you do the calculation like this, the reflection coefficient is equal to load impedance minus characteristic impedance, divide with load impedance plus characteristic impedance. So you're going to get equal to 1. So if equal to 1, that means total reflection occurs. That means all of the incident wave will be reflected back to the source. That means incident wave, and then all of it will be reflected back to the source. Total reflection occurs. Okay. Then, when short circuit happen, the third extreme cases, okay, the third extreme cases is like this. Connected, short circuit. Okay, so this is the source side, this is the load side. Okay, so when the load is short circuit, that means the load is equal to 0. Again, this is not equal to the characteristic impedance. For this case, okay, all of the incident wave will be reflected back to the source, but it is 180 degree out of phase. Okay, so total reflection occurs, but in terms of phase, it is opposite direction. 180 degree phase different between the incident wave and the reflected wave. Okay, so the incident wave and the reflected wave has phase difference for about 180 degree. Okay, so that means all the incident wave will be reflected back to the source. Okay, only in the match circuit that there's no reflection. Okay, in match circuit, all of the incident wave will be absorbed by the load. Okay, so if you ask me, this is the ideal case. The match circuit is the ideal case. This is what we want actually. We want all the incident wave to be absorbed by the load. Okay, because reflection is actually losses. Okay, ideally, we don't want the losses, ideally. Okay, so this is it, the standing wave. Okay, class, can I get your response again? Are you still there?
Yes, Doctor.
Okay. Okay, so this is the standing wave, gelombang berdiri. Okay, in Malay we call it as a gelombang berdiri. So we have asked this standing wave before in the previous semester final exam. Okay, so we have asked in the question before, explain about the standing wave in an open line or shorted line. Okay, so you're going to see that there's two pictures over here. The first one is standing wave on an open line. Open line means it is open circuit, okay, at the load. Okay, so in this case, ZL is not equal to the characteristic impedance. Okay, and we have seen that the reflection coefficient is equal to 1. Okay, as shown previously, open circuit. Okay, reflection coefficient is equal to 1. That means all of the incident wave will be reflected back to the source. Okay, so we want to see how does the voltage and current behaves in the open line. Okay, so standing wave we can see from the perspective of voltage and also from the perspective of current. So now we're going to see both of it, the voltage and also the current. Okay, so you see that in a standing wave, none of the power is absorbed by the load. So that means it's going to be total reflection. The voltage of the wave will be reflected back and there's no phase reversal. Okay, for the voltage, that means the incident voltage has the same phase as the reflected voltage. Okay, for current, okay, current also will be reflected, will have a total reflection. However, for the current, there's going to be 180-degree phase difference between the incident and the reflected current. Okay, and remember the sum of two waves, incident and reflected. So when we mention about the sum, we can see from the perspective of voltage or current. Okay, so the sum of the incident and the reflected current is minimum at the open line. The sum of the incident and reflected voltage waveform is maximum at the open line. So what does it mean? So now we're going to see from the picture. Okay, so you see that from this picture, okay, you see that on the left side is the source, on the right side is the load. Okay, and we see here, we can see from here there are two things. There are two lines. The blue color is the voltage, while the dotted line, okay, the blue line is the voltage, shows the standing wave of the voltage, while the dotted line is the standing wave in terms of current. Okay, so in this case, we're going to see two perspectives of standing wave. The standing wave due in terms of voltage and also the standing wave in terms of current. Okay, so remember, standing wave is the sum of incident and reflected wave. Okay, for example, the blue line. Okay, the blue line shows the summation of incident voltage and a reflected voltage, while the dotted line shows the sum of incident current and a reflected current. Okay, and for the open line, you see that it says that the voltage at the open line is here on the right side. The voltage is maxima. Okay, maxima, we call it as antinoughts, right? And the current at the open line is minimum. Okay, the current is here, the minimum at the open line. Okay, then if we see from this picture, if we move from the open line to the left towards the source, what happened? If we move lambda over 4 from the open line, the voltage becomes minimum or knots. Okay, call it knots, right? Okay, minimum is knots, maxima is anti-knots. Okay, just a name, terms. Okay, so if we move lambda over 4 from the open line, okay, the voltage becomes minimum while the current becomes maximum. And if we move another lambda over 4 distance towards the source, we're going to see that the voltage becomes maximum. Okay, the voltage becomes maximum while the current becomes minimum, and so on, dan seterusnya. Okay, and you see that okay, so from maximum, so from between two maximum, okay, between two maximum is the distance is lambda over 2, and between two minimum, the distance is lambda over 2. Okay? The distance. Okay, this is to show you this statement by half wavelength. Okay, so between the anti-knots and between the knots is separated by distance lambda over 2, half lambda, separuh lambda. Okay, so what is lambda over 2? Half lambda means this one, from two different points. Okay, the distance. And another one is this one, standing wave on a shorted line. Okay, so we have asked this kind of question before. You have to explain what is a standing wave, how does the standing wave behave in a shorted line or open line. So you need to have a simple explanation, and then you can sketch the picture, okay, in terms of voltage and current. Okay, so for a shorted line, okay, shorted line means that the line is at the load side is shorted. Okay, so this is source, this is the load. Okay, so the load is shorted. That means the load impedance not equal to the characteristic impedance. Okay, and the reflection coefficient is equal to -1. Okay, for sure, for a shorted line. So in this case, none of the power is absorbed by the load. The voltage, okay, the reflected voltage is 180-degree different from the incident wave. Okay, from the incident voltage. In terms of voltage, the voltage of the reflected voltage is 180-degree different from the incident voltage. While the current, okay, the reflected current has the same phase as the incident current. Okay, there's no phase reflection, there's no phase reversal in the current perspective. Okay, so the sum of the incident and reflected current is maximum at the shorted line, while the sum of the incident and reflected voltage is minimum at the shorted line. So in this case, we have to see from the picture. Okay, so the picture here shows the standing wave from the perspective of current and also from the perspective of voltage. Okay, so you see that the blue color is the standing wave of the in terms of voltage. The dotted line is the standing wave in terms of current. Okay, so you see that at the load side, on the right side is the load side. Okay, so the voltage is minimum, okay, at the shorted line, and the current is maximum at the shorted line. Again, if we move from the shorted line, the load side, towards the source for about lambda over 4 distance, okay, we're going to see that the voltage becomes maximum while the current becomes minimum. Okay, and if we move towards the source again, okay, if we move towards the source, so within the transmission line, we want to analyze part by part. Okay, so in the transmission line, if we analyze at different part, okay, that means we move towards a lambda over 4 towards the source. Okay, so again, you're going to see that the voltage become minimum while the current becomes maximum, and so on. Okay, and you see that between antinodes, the distance is lambda over 2, while the distance between nodes is also lambda over 2. Okay, so this is the standing wave. Okay, so we have asked this question before in the final exam. So for you should I'm not expecting you to memorize every words. Okay, no, you just need to explain what happened to the voltage and what happened to the current at the load side. What happened? Okay, that's it. And you can draw the picture. You can sketch the picture, something like this. Okay. So this one is among the favorite question in the previous final exam. Okay, about the standing wave. Okay. Then we can move to the next parameter, the VSWR, the voltage standing wave ratio. Okay, it's defined as the ratio of maximum voltage to the minimum voltage of the standing wave on a transmission line. Okay, so it is often called as a VSWR. VSWR is the measure of the mismatch between the load impedance and the characteristic impedance of the transmission line. So the word mismatch here, okay, means that the load impedance not equal to the characteristic impedance. Okay, that means standing wave happens. Okay, and then VSWR can be measured as Vmax over Vmin, the maximum voltage divided with the minimum voltage. So what is the maximum voltage? It is equal to incident voltage plus reflected voltage. The minimum voltage is incident voltage minus reflected voltage. So we're gonna get a parameter without a unit. Okay, VSWR is a parameter without a unit. Okay, and the relationship between VSWR and also the reflection coefficient. So you see that VSWR, the equation is Vmax over Vmin, and the reflection coefficient is actually reflected voltage divided with the incident voltage. And if we combine both of these parameters, okay, we're gonna get VSWR is equal to 1 plus reflection coefficient divided with 1 minus reflection coefficient. Okay, and we can also write reflection coefficient equal to VSWR minus 1 divide with VSWR plus 1. Okay, so this one we rearrange the equations and we can get like this. Okay, so standing wave ratio VSWR with a load is purely resistive, VSWR can be expressed as Z0 over ZL, or VSWR equal to ZL over Z0, whichever give you the VSWR more than 1. Okay, so VSWR, the value is more than 1 in this case. So we can choose any of these which give the value more than 1. Okay, the disadvantage of unmatched transmission line. So there are a few disadvantages. Okay, what is the disadvantage of unmatched transmission line? What is the disadvantages if the load is not equal to the characteristic impedance? What happened? What is the disadvantage? The first one is 100% of the source incident power is not absorbed by the load. Okay, that means there's going to be reflection. The reflection and the re-reflection will cause more power loss. Okay, so mismatch also cause noise interference in the transmission line. Okay, so these are among the type of noise in the transmission line. Okay, so let's do this example. Okay, let's do this example. So for a wait, okay, for a transmission line with the incident voltage EI equal to 5 volt and reflected voltage equal to 3 volt, determine the reflection coefficient. Okay, so reflection coefficient is equal to reflected voltage divide with incident voltage. Okay, divide with incident voltage. So 3 volt divide with 5 volt. So you're gonna get 0.6. Okay. What about SWR? So SWR is equal to SWR or VSWR is equal to Vmax over Vmin. Okay, so it is EI plus ER divide with EI minus ER. Okay, so this is 5 plus 3 divide with 5 minus 3. Okay, so 8 divide with 2, so you're gonna get 4. Okay, simple as that. And then what? And then the input impedance. So input impedance is defined as the impedance at any point on the transmission line. So if you have a transmission line, okay, so at different point, okay, at different point, the input impedance Zin gonna be different. Okay, at two different points, the input impedance will be different. This is different from the characteristic impedance. Characteristic impedance does not characteristic impedance is not proportional to the length of the transmission line. Regardless of the length, regardless of any point, the characteristic impedance of the transmission line would be the same. But for the input impedance, this is a specific impedance at a certain point in the transmission line. So they're gonna be different values. Okay, so Z input is equal to voltage at that point, at a specific point, divide with the current at a specific point. Okay, so we're going to get the input impedance. And the input impedance can be calculated using these equations, okay, for a lossy medium and for a lossless medium. Okay, and again, you don't need to memorize this equation. Okay, you don't need to memorize this equation. So a long time ago, we studied this input impedance using a Smith chart. So Smith chart has been pulled out from the notes, from the lecture notes. We have exclude the Smith charts topic because it's going to take more time for the students to study. So we try to reduce the topics in chapter 5 by excluding about these specific topics. This is also a good topics where the student will learn how to find the input impedance using a given Smith chart, the round charts. So this another thing is other than using the charts, we can use this specific formula to calculate the input impedance. So I move to the next part. So again, this is also input impedance. So input impedance along the transmission line can behave in terms of different characteristics like this. So you see that there are two pictures above and below. Okay, the picture above is for an open circuit. Okay, so for an open circuit, okay, open circuit, that means at the load side is open. Okay, so the input impedance at the load behave like a resistance with maximum value. Okay, so I just want to explain what does it mean by all of this. We have a R, C, L, R, C, L, and so on. So the input impedance at the load side consists of resistance value with the maximum value. And when we move towards, okay, as we move from the load towards the source, okay, you're going to see that the input impedance at different point behaves in terms of capacitance. It becomes more capacitance. The capacitance would be dominant. And then at lambda over 4, the input impedance behave in terms of resistance with a minimum value. Then as we move further, okay, the input impedance has a inductive reactance dominance. Okay, until we reach the lambda over 2, and we're going to get the value in terms of resistance with maximum value. Okay, so this is to show that how does the transmission line behave at different points. Okay, at different points, the input impedance would be different, and which parameter would be dominant, either the resistance, the inductance, or the capacitance. Okay, and if we see from the picture below is for the short circuit. Okay, short circuit. So short circuit, you see that the input impedance at the load side has a resistive value dominance with minimum value, okay, minimum R. And when we move further towards the source, the input impedance has a inductive values dominant. And then at lambda over 4, it becomes the resistive value maximum. And then as we move further, it consists of more capacitance parameter. The capacitance is more dominant, okay, until we reach the lambda over 2 value distance, okay, and the input impedance has more resistive value. Okay, so this is how does the transmission line behaves in terms of parameters. If you remember that the transmission line can be can be drawn using the R, L, C, G parameter, right? So we want to see which of the lump element parameter is dominant when we move from one point to another point. Okay, so this is it. Okay. So the next part is about the antenna. Okay, so antenna also will come out in the final exam. Okay, antenna also will come out in the final exam question. Okay, so antenna is the thing that radiates the electromagnetic wave into the medium. Okay, antenna is a component in the transmission, is a component in the communication system that radiates the electromagnetic wave into the medium. Okay, so if I draw the picture here, okay, if we draw this picture, that means this is the antenna. Okay, the antenna is a component that radiates the electromagnetic wave into the channel. Okay, not only it radiates, but it also absorbs. Okay, it also absorbs the electromagnetic wave for the receiver. Okay, so it can radiate and absorb the wave, okay, from the channel. And this is the equivalent. The first one is a 4-terminal network. Okay, the transmitter. So we have a 4-terminal network here. Okay, so this is the antenna side. Okay, so at the transmitter antenna, and here is the receiver antenna, separated by a space medium. Okay, and here is the load side on the right side. And if you see the picture B and C is the equivalent antenna circuit. Okay, antenna equivalent circuit for transmitter and also the receiver. Okay, so the equivalent circuit consists of the source and the load side. Okay, so the equivalent circuit for antenna is different from one design to another design of antenna. Okay, so different antenna design will have different equivalent circuit. Okay, so we don't need to go through deep into this topic. Okay, because it is enough for you to understand that the equivalent circuit for antenna is depending on the antenna design itself and also the applications. Okay, this is an example of a simple equivalent circuit of transmitter and the receiver. Okay, so the basic operation of the antenna, you see that the antenna radiates the wave in a spherical pattern. Okay, in a spherical pattern. So you see that theoretically, we can see that the antenna radiates the wave in a spherical form. Okay, so you see that this is a spherical form. Okay, this is a spherical wave. Okay, why does it shows a spherical? Actually, if you draw, it is like a spherical. Okay, it's a part of sphere. It is a part of sphere, so it's a spherical form. And when the wave travel at a long distance, we can see that theoretically the wave shows like a plane wave, a straight line. Plane wave is a straight line. So this happens when the wave already travel at long distance. We can see that it behaves like a plane wave. Okay. So initially it is a spherical wave, and later when it travels at a long distance, it becomes a plane wave. Okay. And this is it, my favorite picture. Okay. So after this, you're going to see why I always drawn this picture during my lecture session. Okay. After this, you're going to know, after this, you will know why my favorite picture is very important for you. Okay. This is it. Okay. So I always draw the transmitter and the receiver like this. Okay. And from here, you can see there are many important parameters. Okay, there are many important parameters. So we're going to go through this. So I hope that you can understand that different parameters. Okay, so you see that we have transmitter, we have the channel, we have the receiver. Okay, so and then if you see at the transmitter side, okay, the power produced by the transmitter is what we call as PT. Okay, the output power of the transmitter produced by the transmitter. So this, the power would be put into the transmission line. So this is a cable that connects transmitter and the antenna. Okay, so you see that this cable or this wire has a loss, which is LT. The loss is in terms of attenuations. Okay, when the wave travel into the line, is going to be attenuations. Then the power goes to the input of the antenna is what we call as P in. Okay, the input power to the antenna. Okay, then we have the power that used for the radiation. Okay, for the power that we use to radiate the electromagnetic wave is what we call as P rad. Okay, P radiation. P radiations is the power of the radiated wave. Okay, so basically the input power is larger than the radiation power. And you're going to see that at the antenna side, there's actually a power dissipation. Okay, at the antenna side, there's going to be a dissipated power. Some of the power, a small portion of the power will be dissipated as heat. Okay, so this is P dissipated. And majority of the power will be used for the radiation. And you see that the transmitter antenna has a gain of GT. Okay, so when we transmit the wave along the channel, the wave behave like a spherical wave. Okay, like this, spherical wave. Okay, and we have another parameter, EIRP. EIRP is the equivalent isotropic radiated power. Okay, so basically this is P times G. Okay, P times G is the radiated power, EIRP. Okay, the power multiplied with the gain, we're gonna get the EIRP. So it shows the strength of the transmitted power. Okay. Then we have another parameter, PD. Okay, so PD is a power density. Okay, it defines the strength of the power at a specific location. So PD is a power per unit area. Okay, power per unit area. Okay, so we can measure how much is the PD at the receiver. Okay, the power density at the receiving antenna. How strong does the power at the receiver side? We measure it in terms of the power density, the power per unit area. Okay, power dibagikan dengan luas kawasan. Then we have P out. P out is the output power from the receiving antenna. Okay, So the output power from the receiver antenna that goes through the transmission line. And within the transmission line, there's another losses, what we call as LR, okay? The receiving losses, okay? So you see that the P out goes through the transmission line, and there's going to be losses. And after minus this, after subtracting with the losses, we're going to get PR, okay? Power received by the antenna. So PR, so P out minus LR, we're going to get PR, okay? P out minus the losses, you're going to get the PR. Similar with this side, so that means P transmitter minus LP, we're going to get P in, P input, okay? So the losses needs to be subtracted with the source power, okay? Okay, so now we're going to see the antenna efficiency, okay? So antenna efficiency is measured as P radiation divided with the P input multiplied with 100%, okay? Remember that the input power, some of the input power will be dissipated as heat, and majority of it will become the radiated power, okay? So efficiency is equal to radiation, P radiation divided with the P input multiplied with 100%. And remember that P input is equal to P radiation times PD. So PD here is not the power density, so this is a dissipated power. So don't be confused. It's different from this PD. The PD here in this picture is a power density. It's a different thing. Okay. While this one is actually P dis. So if for me, I like to use a P dissipated. Okay. So another thing is that we can see the antenna can be represented in terms of resistive value. Okay, so if you see that this is the picture of the antenna, where it consists of R RE and also RR over here, R radiation. Okay, RE is the effective resistance, RR is the radiated resistance. Okay, and we can also measure the efficiency in terms of resistance. Okay, so this is R radiation divided with R radiation plus R effective of the antenna, and you should multiply it with 100% so that you can get in terms of percentage. Okay, so this is the second equation. The first equation to calculate the efficiency is this one. Okay, and the second equation to calculate efficiency using the resistance value. Okay, and this is the isotropic antenna. Isotropic antenna is a point source that radiates electromagnetic energy at a constant rate in all direction. Okay, so if you see from this picture, isotropic antenna is actually a theoretical antenna. It does not exist in the real world. Okay, it is a theoretical concept of antenna. So when we design a real antenna, normally we will use the isotropic antenna as a reference. Okay, so isotropic antenna is a reference antenna. It's actually a theoretical antenna that does not exist actually in the real world. Okay, so if you see in this picture, the isotropic antenna is this one actually, the point source, the center. okay, where it radiates the wave in all directions. Okay, so when it radiates the wave in all directions, we can see that the wave looks like a spherical wave, like a sphere. Okay, and there is a few characteristics of the isotropic antenna. The first one is that the wave is radiates in all directions. Okay, the first characteristic of the isotropic antenna is the wave is radiates in all directions. Okay, the second characteristic of isotropic antenna is about the gain. The gain is unity. Okay, so there are two different gain for the antenna. The first one is a power gain. Okay, the other one is directivity gain. Okay, so for both gains is equal to 1. Okay, the gain is equal to 1. And you might wonder what's the difference between the directivity gain and also the power gain. Okay, so directivity gain D or GD. Sometimes if you see in other literature books, they use the terms GD, directivity gain. Okay, so either you want to use GD or D, is not a problem. Okay, so directivity gain is equal to the power density. Okay, this is a power density of a real antenna divided with the power density of an isotropic antenna, P reference. So the reference antenna is usually the isotropic antenna. So imagine that if I have a real antenna, okay, and I want to measure the power density at a certain distance. Okay, so my antenna has a specific gain. It has a specific gain. And if I want to compare with the isotropic antenna, okay, isotropic antenna has a gain of equal to 1. Okay, and at a certain distance, at the same distance D, I found out that the power density is P ref. Okay, so the ratio of both of these is what we call as the directivity gain. The difference, the ratio of power density of a real antenna divided with the reference power density by the reference antenna at the same distance is what we call as the GD. Okay, so power density is a watt per unit area. Okay, so actually we are comparing two different kind of antenna, the real antenna and the reference antenna. And normally for the reference antenna, we use the isotropic antenna. Okay, so once we know the directivity gain, then we can measure the power gain. The power gain, okay, is known as GP. Okay, so before this we have GD, directivity gain. The other type of gain is equal to power gain. Power gain is equal to directivity gain multiplied with the antenna efficiency. Okay, multiplied with the antenna efficiency. So for this case, for most of the time, okay, GP would be less than GD. Okay, only if the efficiency is 100%, then GP equal to GD. Okay, but for most of the time, you're gonna see that the power gain is less than the directivity gain. Okay, so antenna radiation pattern. So this one, antenna radiation pattern. So this is the 3D radiation pattern of the antenna. So normally when we design the antenna, what among the important parameters are, we want to see the what we call as a radiation pattern. Okay, so the radiation pattern shows the direction of the wave and also the strength of the wave at specific angle. Okay, so there are two kinds of radiation pattern. We have the 3D radiation pattern, like in this slide. In this picture is a 3D radiation pattern. We also have a 2D radiation pattern. Okay, so for the radiation pattern, as I said, that we want to see the direction of the wave at which angle, and also the strength of the wave. So if you see from this picture, okay, the antenna is actually located at the center. Okay, so the antenna is located at the center of the radiation pattern. And from this example, we can see that most of the wave, okay, travel on the right direction. Okay, most of the wave is travel towards the right direction over here. Most of the wave goes to the z-axis. Okay, z-axis in this example. Okay, so majority of the wave goes through that direction, through the z-axis directions, and we can say that if majority goes to that side, so we can form the what we call as a major lobe. Okay, the terms is major lobe, means that majority of the wave move into that directions. And we have another terms, what we call as the back lobe. Okay, 180 degrees from the major lobe is what we call as the back lobe. Okay, remember that the wave that travel into the wireless medium is unguided. That means the wave can travel in many directions. Okay, so the wave that travel back at the back side, this is what we call as a back lobe. Okay, and we also have what we call as a side lobe. Okay, we also have what we call as a side lobe. Another terms is side lobes. Okay, side lobe. So this is just the terminology of the radiation pattern. So if you see that some of your friends that do the FYP project, if your friends do antenna project, of course your friend needs to analyze the radiation pattern of the antenna, either through the simulation or through the experimental at the lab. Okay, so this is among the important things when we design antenna. We want to see how good is our antenna through the radiation pattern. Okay, in terms of strength, okay, you can see that the strength of the wave in terms of watt per area, for example. Okay, you can also measure the watt per area. Okay, so this graph actually can also show the strength of the wave. For example, the power density, for example. Okay, and we have another parameter, what we call as a far field region. Okay, far field region is a region from the antenna. Okay, so far field region is a region of area. Okay, at a distance 2d square over lambda from the antenna. Okay, so if we measure the distance 2d square over lambda from the antenna, that is what we call as a far field region or the Fraunhofer region. So antenna power that reach the far field region will continue to radiate outwards and never return back to the antenna. So what does it mean? So if we go through this picture, okay, you see that the antenna is over here, You see that the antenna, the center of this picture, and you see that far field region is the distance after after this, after 2d square over lambda. This is what we call as a far field region. Okay, the far field region. So the wave that already reached the far field region will go straight and never return back to the antenna. Okay, and the region near the antenna is what we call as a near field region. Okay, is a near field region. Near field region is what we call as a Fresnel region. Okay, so it is the region within the distance 2d square over lambda. Okay, so d 2d square, d is the diameter of the antenna surface, lambda is the wavelength. Okay, so the d here is the diameter of the antenna. So we're going to see this example later about this. Okay, and this is it, the example. Okay, class, can I get your response? Are you still there?
Yes, Doctor.
Okay.
Yes.
So for example 6, okay, for example 6, find the far field region, find the far field distance for an antenna with maximum dimension 1 meter. Okay, so the dimension here means that the diameter, okay, the d parameter, operating at frequency 900 megahertz. Then repeat for a different frequency, 10 gigahertz. So the first question, you need to find the far field distance using a 900 megahertz frequency. Then repeat again, find the far field distance using 10 gigahertz. Okay, so far field region, as we have learned, that it is equal to 2d square over lambda. Okay, so we have been given the d parameter, the dimension or the diameter is 1 meter. Okay, so in this case, don't be confused. The dimension here means the diameter of the antenna surface. Okay, so in your lecture notes, okay, we assume that the surface of the antenna is in the form of circle. So imagine like a parabolic antenna. Okay, you can imagine like a parabolic antenna, like the astro antenna. The astro antenna is a parabolic shape, right? So the surface of the antenna is actually a circular shape. Okay, and here the distance or the dimension here is d parameter. Okay, so in your lecture notes, we always use the parabolic antenna as an example. So the surface of the antenna is a circular form, it's a circle shape. Okay, so from here we need to find the lambda, because we need to use a 2d square over lambda, right? So lambda is equal to c over f. Okay, c over f. So we're going to get the lambda parameter in terms of meter. Okay, so the far field distance 2d square over lambda, lambda is c over f. Okay, so if c over f, that means it's going to be f over c, like this. Okay, so you multiply with f over c. Okay, and then you put inside the value 2 times d square. So 2 times 1 meter square times 900 megahertz divide with the speed of light. Okay, so you're gonna get 6 meter. Okay, so class, don't be confused with this part. Okay, if you divide with lambda, if you divide with c over f, that means you're gonna multiply with f over c, like this. Okay, so this is just a mathematics. Okay, so you put inside the value. So if you don't want to confuse like this, you can solve this parameter first, C over F. Okay, so this is 900 mega times 10 power of 6 divide with speed of light. Sorry. Yeah. So this is speed of light 3 times 10 power of 8 divide with 900 times 10 power of 6. Okay, so you're gonna get this 6 meter. Okay, and then if we change the frequency to become 10 gigahertz, okay, so if we change the frequency to 10 gigahertz, what happened? So the far field distance is equal to 2 times the diameter square multiplied with the frequency 10 giga divided with the speed of light. So we get the far field distance is 66.67 meter. Okay, so if we use the different frequency, the higher the frequency, the far field distance becomes longer. Okay, the higher the frequency, the far field distance will be longer. Okay, that means the wave needs to travel until 66.67 to reach the far field region. Okay, compared to the if you use a 900 mega. Okay. Okay, the field intensity and power density. Okay, so this is the most important parameter, and it will come out in the exam. Okay, about the electric field and magnetic field, and also the power density parameter. Okay, so you see that here the field, when we talk about electromagnetic wave, that means we have the electric field and also we have the magnetic field. Okay, because we use the electromagnetic wave. Electromagnet means that we have electric field and also we have the magnetic field. Okay, so the electric field, E field, is measured as square root of 30 times P times G divided with the distance from the antenna. Okay, the distance from antenna. So you might wonder which P is this and which G is this. Okay, so there's a two combination for power and gain. If we use the P radiation, we need to multiply with the directivity gain, GD. If we use the input power, we need to multiply with power gain. Okay, so this is the two combination. Okay, and for the isotropic radiator, remember isotropic radiator, the GD is equal to 1, GP also equal to 1. Okay, so if I go back to the previous slide, this slide, okay, for the isotropic antenna, the first characteristic is that it radiates the electromagnetic wave in all directions. And the other one, the other characteristic is that the gain is equal to 1. Okay, the power gain and also the directivity gain equal to 1. And for this case, okay, for this case, that means we can put G is actually equal to 1. So that means multiplied with 1. Okay, so 30 times P. So since the gain is 1, so that means we can make it as 30 times P only. Divide with R. And the unit for electric field is volt per meter. Okay, volt per meter. Okay, so this is for isotropic antenna. Okay, for other types of antenna, we can use this. Okay, it's the same equation. So we just play around with the P and G parameter. Okay, and if you want to measure the what we call as a power density. So the power density, there are a few equations, there are a few formulas that we can use to calculate the power density. Okay, power density is the power per unit area. Okay, power dibahagikan dengan luas kawasan is a watt per meter square. So the first equation we can use E times H, the electric field multiplied with the magnetic field. Okay, so this is a volt per meter multiplied with ampere per meter. Okay, so you're gonna get a VA over meter square. Okay, VA over meter square. Wait, So this is watt per meter square. So VA over meter square or watt per meter square. Okay. So this is the first equation. The second equations for power density is P times G divided with 4 pi r square. Okay. So I can say that this is the second equation. Okay. So P times G, as I said that either we can use P radiation multiplied with directivity gain divide with, sorry, okay, either we can use a P radiation times GD or P input multiplied with GP. Okay, the combination of P and G. Okay, so you see that we divide with 4 pi r square. This 4 pi r square is actually the surface area of a sphere. Okay, if you remember, if you learn in mathematics, the surface area of a spherical is can be measured as 4 pi r square. Okay, 4 pi r square. Okay, so you see that this is the second equations, and there's another equation, the third equation over here, power density, E times H equal to E square over 120 pi. Okay, so this 120 pi, there's a mathematical definition for this one, 120 pi. 120 pi is for the wave that travels in the free space. So the wave, if we use a free space as a channel or the medium, so we can use this parameter. So this 120 pi is also depending on the type of dielectric constant of the medium. Okay, since we use a air medium or the free space, so the epsilon r has a certain value, and when we measure it, it can be the 120 pi. So 120 pi is not a magic number. There's a mathematical definition for this. So this is, we can also use E square over 120 pi. So this is the third equation. Okay. So if you see from this picture, the sphere, the spherical picture on the right side here. So you see that, for example, the antenna is in the center, for example. Okay. So you can measure the power density over here at distance R1. Okay. At distance R1, you can measure the power density in this area. And if we move further away from the antenna at distance R2, okay, we can also measure the power density. Okay, power density at distance R equal to R2. Okay, the distance is R2. Okay, so you're going to see later that the further away we go from the antenna, the power density will become less. Okay, that means power density at distance R1 is higher compared to the power density at distance R2. Okay, so power density at the longer distance would be smaller compared to the power density at a shorter distance. Why is it like that? Okay, again, we have to go back to the equations. Okay, so you see that the power density is, if you see from this second equation, the power density is depending on the distance from the antenna. The far away from the further the distance, the power density will become less. That means the strength of the wave at the longer distance will be smaller compared to the strength of the wave at shorter distance. Okay, so this is explained in terms of this graphical picture. Okay, so this slide wants to show you that the power density become less as we move further away from the antenna. Okay, so you see that the antenna is located, for example, here, the antenna is located here, and at distance R, okay, you're going to see that the power density is measured in terms of this area. Okay, so the power is scattered in this small area. However, when we move further away, okay, when we move further away from the antenna, you're going to see that the surface area becomes larger. The surface area becomes larger. So the power will be distributed in this bigger surface area. Okay, the surface area becomes bigger. And when we move further away from the antenna at distance 3R, the surface area would be much bigger, 9 times. Okay, so previously is 4 times because it's a 2R, and then 3R, so the power will be distributed in a 9 times of the initial area. So the area becomes bigger. So that means the power density would be smaller. Okay, so this is to show you the relationship between the distance and also the power density. Okay, and we're going to do this example. So there are many examples after this. Okay, so class, can I get your response again? Are you still there?
Yes, doctor.
Okay, so let's do this example, example 7. Okay, so example 7, an isotropic radiator is radiating 1 watt of power. Okay, is radiating 1 watt of power. What does it mean? So it means that this is P radiation, okay, into the free space. Calculate the electric field intensities, okay, find the E field and power density, PD. So you need to find the E parameter and power density parameter at a distance 1 kilometer. Remember, class, when you are given this kind of question, you must convert kilometer into meter. That means R equal to 1000 meter. Okay, so you have to be careful about this. Remember, all the equations should use the standard unit. Okay, we must use the meter, not kilometer. Okay, so you are given P radiation, you are given the distance 1000 meter, and also the gain. So how can we know the gain? So since this is an isotropic radiator, that means the radiation, the directivity gain is equal to 1. GP also equal to 1 because we are using isotropic antenna. Okay, so therefore E field is equal to P radiation square root of 30 times P times G. So if we use the P radiation, that means this is a GD. Okay, so divide with distance from the antenna is 1 kilometer. So we put here 1000. P radiation is 1 watt, gain is 1. Okay, so we get 0.0055 volt per meter. Okay, volt per meter. Or you can write V over M, volt per meter. Then the power density, okay, the power density is equal to E square over 120 pi, and then you can put it 0.0055 square divided by 120 pi, and you're gonna get this one. Okay, you can also use a different equation if you want. Okay, so this is also P times G. So you can use the same P radiation times directivity gain divide with 4 pi r square, and you're gonna get the same answer. Okay, so this is 1 times 1 divide with 4 pi. This is 1000 square. Okay, try use your calculator whether you can get the same answer or not. So 1000 square times 4 pi 1 divided with answer. So you're gonna get 7.9577 times. So you're gonna get the same answer. Okay, you're gonna get the same answer. Okay. So if you have question, you can ask. Otherwise, I will move to the next example. Example 8. Okay. So class, if you have question, please ask question. If you don't ask question, I assume that you understand this example. Okay. So example 8, electric field intensity is 20 millivolt per meter. So this is the E field. Is measured as the electric field strength of an isotropic radiator. So we are using isotropic antenna. If the radiator is radiating 1 watt of power, so you see that radiation power. So this is P radiation. Okay. Find the distance at which the measurement is taken. Find the distance. So you see that class, we have the isotropic radiator. Okay, so I suggest you to sketch your own drawing so that you can have more understanding. Okay, so you are given an isotropic radiator which has the P radiation. So the P radiation is equal to how much? Field strength 1 watt. Okay, so since this is isotropic radiator, that means GD equal to 1, GP also equal to 1. Okay, and at a certain distance, okay, at a certain distance, we measure the E field to become 20. This is 20 millivolt per meter. The question now is how much this distance? How much? Okay, so therefore E field is given, P radiation gain is given, so we can use this E field equations. So E field is equal to 30 times P radiation times G divided with R. Okay, so if we change the value R is equal to square root of 30 times P radiation times G divided with E field, electric field. So we can put the parameter here, square root of 30 times 1 watt of radiation power times gain 1 divide with the electric field, and we're going to get this value, 273.86 meter. Okay, so the distance is 273.86 meter. Okay, and then what? Example 9. Okay, so this example 9 almost similar with the question in the final exam later in this semester. Okay, so so you see that this example, a field strength of 15 millivolt per meter is measured from an antenna with a gain of 1.5. Okay, so that means this is a real antenna. Okay, and then calculate the field strength of an isotropic antenna if we use an isotropic antenna. So now the issue is like this. Okay, so if I draw the picture, let's say that this is my antenna. Okay, this is my antenna, and my antenna has a gain equal to 1.5. Okay, and it has a specific P radiation. Okay, and when I measure the electric field at a certain distance r, okay, I found out that the E field, electric field, is equal to 15 millivolt. 15 millivolt millivolt per meter. Okay. Now the question said that if we change into isotropic radiator, okay, isotropic radiator has a gain equal to GD is equal to 1, GP is equal to 1. Okay, and we have a P radiation, and then the distance is R. Now the question said that how much is the E field? Okay, so for this case, what is the assumption that we know? So in this case, we should understand that the radiation power should be the same. Okay, the radiation power should be the same. The distance should be the same. Okay, because we want to compare. Okay, we want to compare side by side. Okay, we are using the same power, the same distance. Find the E field. Okay, so you see that how does the answer looks like? So you see that you are given the E field and you are given the gain of the antenna. Okay, so the E field is measured as square root of 30 times G, 30 times P, sorry, square root of 30 times P radiation times the gain. So this is actually the directivity gain. Okay, and then you see that 30 times P radiations. So we put outside, okay, we put outside the parameter that has been given in terms of value. Okay, so we put outside E divide with square root of G. So why do we need to do like this? Because this is the given parameter. Okay, this is the given parameter from the question. Okay, given parameter from the question. And the parameter on the left as I said, that is assumed to be fixed for two different antennas. Both antenna use the same P radiation and the same distance. Okay, so we assume that this becomes A parameter, assuming is a A variable equal to E over G. Okay, so therefore E over G, A is equal to E field divide with the gain. So you're going to get 0.0122. Okay, so now we want to find out the E field. Okay, we want to find out the E field if we use the isotropic antenna. Okay, so now we have the A parameter. We already calculate the A parameter. A parameter is this one. Okay, so A parameter is equal to square root of 30 times P radiation divide with R, okay, which is equal to E over square root of G equal to 0.0122. Okay. So now when we use the isotropic radiator, so now we change the antenna. Okay, class. Initially we have a real antenna. Now we just change it into isotropic antenna. Okay, so when we change the antenna, the isotropic antenna has a gain of 1. And we need to find the E values. Okay, so E is equal to parameter A multiplied with square root of G. Okay, from here, from this, from the equation that we have found previously. Okay, from here, from equation 1, E parameter is equal to A multiplied with square root of G. Okay, so therefore, the new E parameters, electric field parameter, is equal to A. A is the thing, is the parameter that we have calculated. Okay, so both new antenna and the isotropic antenna and the real antenna has the same A parameter. We multiplied with the gain. The gain is different now. The gain is equal to 1. Okay, the gain is equal to 1. So therefore, we're going to get this E parameter is equal to 12.22 millivolt per meter. Okay, so 12.2 millivolt per meter. Okay, so this is the answer. So you see that from here, we can see the difference. The E field from the isotropic antenna is less than the E field produced by the real antenna, which is 15. Why? Because the gain of the isotropic antenna is equal to 1. Okay, so at the same distance, okay, when we measure the electric field at the same distance, the electric field produced by the isotropic antenna is less because the gain is equal to 1. Okay, and in this case, we make sure that the distance and the radiation power is the same. We must fix it, okay, because we want to compare side by side. When we want to compare side by side, we must make sure that certain parameter must remains the same. In this case, the power same, the distance is the same, but the gain is different because we use a different antenna. Okay, so the E field produced by the isotropic antenna becomes less because the gain of the isotropic antenna is equal to 1, whereas the real antenna has a gain of 1.5, larger than the isotropic antenna. Okay, and we're going to see another example so that you can have more understanding about this. Okay, so the final exam question looks like this. Okay, the final exam question, later you're going to see that it looks like this. You will be given a parameter of a real antenna, and then you will be given the E parameter, electric field parameter. And assuming that we change the antenna into isotropic antenna, how much would be the electric field? Okay, so the final exam question looks like this. Okay, and we're going to see another example so that you can have more understanding. Okay, so example 10, calculate the power density at 10 kilometer away. Okay, so this is 10,000 meter. Remember that. From the isotropic antenna that radiates 5 watt of power. Okay, so this is P radiation. The electric field strength is found to become 3 times stronger if we change the radiator into a real antenna. Find the gain of the antenna in dBi. dBi is the decibel unit. So this is the same as dB. Okay, dBi is a decibel with respect to isotropic antenna. So dBi. So antenna usually we use a dBi instead of you just write dB. So normally the formula is the same as dB to measure the decibel. Okay, the dBi means decibel with respect to the isotropic antenna. So that's why dBi. Okay, so the story is like this. So initially you have the isotropic antenna. That radiates electromagnetic wave in all directions. Okay, and you are given the P radiation. Okay, is given as 5 watt. Okay, so we know that isotropic antenna has a gain equal to 1. Okay, so both GP and GD, so GD equal to 1, GP also equal to 1. And it said that at distance R equal to 10,000 meter, the E field is, okay, so it said that this is the E field. Okay, and then what? Now the question said that if we change into a real antenna, okay, a real antenna has a specific gain. I don't know how much is the gain, okay, but we are using the same radiation power. Okay, and we are measured at a distance, same distance, R equal to 10,000 meter. And it said that if we change into real antenna, it's gonna be 3 times. Okay, so the question asks you to find how much is the gain. Okay, so first of all, we need to know about the isotropic antenna. Okay, so we are given the P radiation, we are given the distance, we are given the distance. We know that for isotropic antenna is equal to 1. So for E field, we can find the E field actually. Okay, we can find the E field is equal to square root of 30 times P radiation times G. Okay, divide with distance. So 30 times 5 watt times 1 for isotropic antenna, divide with 10,000 meter. So we're going to get 0.0012 volt per meter. Okay, so this is 0.0012 volt per meter. Okay, and then what? The solution give you PD. So PD is not asked in the question actually. So the power density is not asked in the question, but the solution just give. So the solution give you the answer. If you want, if let's say you want to find the power density, you can use like this. Okay, but the question not asked to find this actually. So power density, you can use a E square over 120 pi, or you can also use a PD equal to P times G divide with 4 pi R square. You can get the same answer. Okay. So there are a few formulas to find the power density. Okay. So in this case, it uses a E square over 120 pi, and we're gonna get this power density. Okay. Now what? Now, so I make a line over here so that we can separate the things. So after this, we're going to see that if we change the antenna, the electric field becomes 3 times. Okay, the electric field becomes 3 times. And this is equal to 30 times P radiation of the new P radiation multiplied with the gain of the new antenna divided with the distance. Okay, in this example, we must make sure that the P radiation and the distance should be the same because we want to compare side by side. Okay, the issue now is we want to find the G parameter. Okay, so if we rearrange the equations, okay, if we rearrange the equation, 3ER equal to square root of 30 times P times G. So G is equal to 3ER square divided with 30 times P radiation. And we put inside the value 3 times 0.0012. This is the electric field. And this is the distance, 10,000 meter. And then square. Divide with 30 times 5 watt. So you're going to get approximately equal to 9. Okay, approximately equal to 9. Then, in terms of decibel, you can make it as 10 log of 9, you're going to get 9.5424 decibel. But the decibel is dBi. dB with respect to isotropic radiator. Okay. So in order to achieve, so you see that class, in order to achieve electric field of 3E at distance 10,000 meter, I need to have the gain, in this case is GD, in this case, equal to 9. If I have gain equal to 9, I can achieve electric field for about 3 times than the isotropic antenna at distance 10,000 meter away. Okay, so I need at least GD equal to 9 in order to achieve electric field 3 times larger than the electric field produced by the isotropic antenna. Okay, so 9, or this is also equal to 9.5424 dB with respect to isotropic antenna. Okay, and then what? Let's do another example. Another example is later. Okay, example 11 is later after this. So the next parameter is EIRP. EIRP is power multiplied with the gain. Is the equivalent power that an isotropic antenna would have to radiate in order to achieve the same power density in a chosen direction at a given point as another antenna. So if you have two antenna, isotropic antenna and the real antenna, so this is equivalent to the power that needs by the isotropic antenna to achieve the same power density as a real antenna at a specific distance. Okay, so for this case, as I said that there are two combinations. So EIRP is actually power multiplied with gain. But which power, which gain is this? So there are two combinations. Either you want to use P radiation, you have to multiply it with the directivity gain. The other one, if you want to use a P input, you have to multiply it with power gain, G. Okay, so EIRP is in terms of watt. Okay, for example, here I use a P radiation times directivity gain. So we get P radiation times directivity gain. So we get the value in terms of watt. And if we change into decibel, 10 log of EIRP, so we get in terms of dBW, dB watt. Okay. And if you want to use a P input, okay, so EIRP can also be measured as P input multiplied with the power gain. The unit is watt. So we get, in terms of decibel, 10 log of P in times GP. So we get the value in terms of dBW. Okay. So EIRP shows the strength of the transmitted wave. Okay. In terms of watt. Okay. So therefore, from the previous power density equation, okay, we can rewrite the power density equations. If you remember previously that the power density in the previous slide, it is equal to P times G divided with 4 pi R square or D square. So don't be confused. Sometimes it use D, sometimes it use R. Okay, so R square is the same thing as D. So don't be confused. So the term P times G is either we use a P radiation times directivity gain or P input multiplied with power gain. Okay, remember the terms EIRP is power times gain. Okay, and remember the distance here is in terms of meter. Okay, so you see that if output power, okay, so this is if we have a loss, if we have a loss, that means P times G divided with the losses. So we're going to see about this later. Okay, we're going to see about this parameter later. And maybe we can have we can do this example first. Example 11, a probe measured of 2 microvolt per meter of a field strength 200 kilometer away from the parabolic antenna with a directivity gain of 1000 and efficiency of 0.85. So you are given the E field, okay? You are given the distance R, which is 200,000 meter, okay, away from the parabolic antenna. And you are given the directivity gain, GD, and the efficiency equal to 0.85, or this is 85%. Okay. Find the power gain, GP. So power gain, GP, is equal to direct efficiency multiplied with directivity gain. Okay. So 0.85 multiplied with 1000. So you're going to get 850. Okay. The next question asks you to find the EIRP. So it is a P times G. Okay. So P times G means that P is not given. Okay. So in this case, if you see that power is not given, but we know the E field. So we can use the electric field equations. We can use the electric field equation to find the EIRP. Okay, so EIRP here is P times G. Okay, so since we want to know how much is this, okay, so EIRP is equal to E times R square divide with 30. Okay, so 2 micro volt per meter of electric field times 200,000 meter. Remember, class, don't use kilometer. Don't use kilometer, use meter. So you have to use 200,000 and then divide with 30. So you're going to get 0.0053 watt. Okay. Then the question asks you to find the P radiation. So once we know the EIRP, we can find the P radiation and also the P input. Okay. So we know the EIRP, we just need to divide with the gain so we can get the power. Okay. So EIRP divide with the directivity gain, we're going to get P radiation. Okay. Which is 0.0053 divided with 1000. So we're going to get 5.3 microwatt. And if you want to find the input power, it is EIRP divided with the power gain. So 0.0053 volt per meter divide with 850 that we already get from the previous question. And we're going to get 6.2 microwatt. So you're going to see that the difference, P input, is larger than the P radiation. The difference is actually the dissipated power as a heat. Okay. And the next question say that find the distance of the probe if we change into isotropic antenna. Initially is a parabolic antenna. Now we change into isotropic antenna. Used for the same amount of field strength. Okay. So now initially it's like this. So 200,000 meter. So we get this E field is 2 microvolt per meter. So now if we change into isotropic antenna, okay, how much is the distance in order to achieve the same E field, 2 microvolt per meter? The issue now is the gain GD is equal to 1, GP is equal to 1. So logically, we can say that the distance is going to be shorter. Okay. So you see that here, in order to find the distance, we can use the E field equations. From the from the electric field equations, we can find the R parameter. Okay, we just swap with this one. So R is equal to square root of 30 times P radiation times, so this is actually times G, GD. So GD is equal to 1. Okay, so this is actually times 1. Okay, so times 1. So square root of 30 times 5.3 microwatt times 1 divide with 2 microvolt per meter. Okay, so 5.3 from this. Okay, so we're going to get 6304 or 6,304 meter. Okay, so we're going to get this value. So that means the distance is much shorter. If we use a real antenna, we're going to reach up to 200 kilometer. Okay, but now it becomes 6.3 kilometer only. Okay, so you see that here the distance is only 6.3 kilometers, 6304. Okay, 04 meter. Okay, in order to achieve the same electric field. Okay. But if we measure at 200,000 meter away, the electric field will become much, much smaller. Okay. If we use a 200 kilometer away distance, the value of electric field will become much, much smaller compared to 2 microvolt per meter. Okay. So I think we should stop until this example, and we're going to continue this example next week. Next week will be our last class. So we're going to take the attendance now. So you can open your QR code. Open your QR code. You can scan the attendance. So I think next week you have to do the demo. So actually in our schedule, this week should be the demonstration of your prototype, transmitter prototype. But since I assume that we have a holiday in the middle, right? So I postponed the presentation to be next week. Okay, I postponed the presentation to be next week. Or if you need more time, you can actually do the demo during the study week. Okay, if you need more time. Okay, so I will give you the schedule of demonstration later after this. Okay, I will give the schedule later. And remember, you should return back my FM receiver, the radio receiver. You should return back to me by next week. Okay, so by next week, please return back my radio receiver. Okay. Yeah. So you can scan. Wait. Needs a few seconds. After you scan, you can go to anywhere you like. Okay. And remember about the report submission and also the quiz. Okay. I already put it in the author. Okay. About the task number 3 submission, report submission. And also the quiz, online quiz would be on Friday morning. Okay. The topic would be AM, amplitude modulation only. Okay, there are going to be 20 objective questions. They're going to be theoretical question and also calculation question mixed up. Okay, so 1 marks for each of the question. So total 20 marks. 20 marks would be converted into 5% of your coursework marks. Okay, so I guess that's it for today. See you again next week. Okay, bye-bye.
Thank you, Dokter.
Okay, welcome.
Thank you, Dokter.
Okay,
Selamat
welcome.
Hari Raya, Dokter.
Selamat Hari
Okay,
Raya,
selamat
Dokter.
raya semua. Okay.
Thank you, Doctor.
Okay, welcome. Okay. So stop sharing.